This is a video introducing the work of Team 42 for the Cluster and Cloud Computing assignment for 2020. Here is a slide with our names and primary responsibilities. Before getting into the architecture of the system, I just want to briefly talk about our system's Ansible deployment. For our Ansible scripts, we have it such that once the SSH key related setup is complete, we can simply execute the run script using the command run.sh-i to initialize the cluster. The script is designed to be executed multiple times. We also use tags to isolate the configure section such that when the -c flag is passed, the configure playbook will be executed against the virtual machines which are currently provisioned. This is achieved with the help of an OS server info task, which is able to query the IP addresses of VMs from MRC Cloud. This allows us to initialize once and update just the non-stable or changing aspects of our deployment. To speed up deployment, we configured Ansible to use pipelining and SSH persistent connections. We also made the instance creation asynchronous as we identified that it is a major bottleneck in the initialization process. Additionally, we configured fully qualified domain names for our CouchDB instances using Docker Compose files, such that our existing CouchDB cluster is immediately available after instance initialization. The deploy couch role is also able to initialize a CouchDB cluster when volumes are not preserved. See the end of this video for the Ansible execution process. This is a diagram which shows the components of our system. Let's start on the right. We have continuous deployment for our system, such that we don't have to manually deploy the changing services on every change to the codebase. When a developer or team member pushes to our GitHub repository, several GitHub action tasks are launched. As we were concerned about exceeding the 3 minutes of our GitHub Teams plan, some of the tasks are delegated to self-hosted runners. When the runner builds the Docker images for our Harvest, App, and MapReduce services, the images are pushed to a registry on GitLab. Then, we have a Watchtower instance on each node which watches for changes in the registry. When an image is updated, the corresponding containers are updated also. This means that we don't have to rerun Ansible each time that we update the code. We have several containers which run simultaneously on one node. One is CouchDB in a clustered setup. Another is the Harvester, which harvests tweets and does the sentiment analysis. We also have App, which hosts the frontend and provides the backend RESTful API routes that the frontend consumes. Caddy is used to reverse proxy the app and provide self-signed HTTPS certificates for the internal IP addresses. This is largely a leftover, as we initially planned to demo the app using internal IP addresses. However, for the sake of convenience, we decided to add an Nginx reverse proxy, shown at the bottom of this diagram, to expose the app through a public IP address and domain. The app subdomain is also load balanced. The reverse proxy is hosted on a private project in the non-internal Unimelb zone on Melbourne Research Cloud. We have 4 nodes in our cluster. On the left of this slide, we have GitHub Actions and GitLab Registry. On the right, we show the services which are running on the master node. To harvest as many tweets as possible, we use the Stream API to observe Australia. However, we soon found that with the same bounding box, different API keys get exactly the same tweets. Hence, we make them watch different states while one of them still watches the whole of Australia. As the harvest progressed, we found that most tweets with coordinates are from users who don't protect their timeline and have geolocation enabled. So we changed the harvester to only harvest these users' friends and timeline. This allowed us to harvest geolocation tweets with high probability. On this slide, we show a diagram which provides an overview on how the harvester instances communicate with each other. As you can see, this is a master and worker model. This is a single master instance, which stores its address info and token in the database and gets unfinished tasks like to harvest user timeline or to harvest users' friends, and waits for connections from workers. There are as many workers as the number of available API keys, since it is the easiest way to manage Twitter API limits. A worker gets the master's info from the database and requests tasks according to its remaining rate limits. Once it finishes the task, it stores the documents to CouchDB, and the view will be updated automatically. Let's now move on to the website. So sign in. All right. We have several sections of our website: summary, keyword search, sport, exercise, and sentiment. As you can see from the summary page, we have harvested over 400,000 tweets from more than 480,000 users. On the left is a line chart showing the number of tweets per the hour of day. From this, we can see that the number of tweets drops off in the early morning. Then, we begin to see a gradual increase from 4 a.m. to 5 a.m. and a sharp increase from 6 to 8 a.m. It peaks at around 5 to 8 p.m., which makes sense as most people would have finished work by this point and have more time to socialize. Again, the number of tweets drops off as we approach midnight. On the right is a bar chart showing the number of tweets per the day of week. As expected, there are relatively more tweets on Friday and the weekend when compared to other days. However, it is unclear as to why we have a gradual increase of tweets as the week progresses. This perhaps suggests that people are busier early in the week when they return to work. However, this will not be conclusive without further analysis. Also, if we inspect the element here and view the requests, we should see that the responses were served by different nodes from the X internal header shown here. So this one is 132.206, and the following one is 131.24. Now, let's move on to keyword search. In this choropleth map, an area is shaded darker when the value for that area is larger. Currently, we're displaying the number of tweets for each area, not filtered by keyword. As the table of the number of tweets indicate, capital cities tend to have a large number of tweets. Let's now focus and zoom in on the Melbourne CBD. As you can see, Melbourne has more tweets than surrounding areas, indicated by a darker hue of blue. Let's now click on Melbourne. When we click on an area, we should see some indicative tweets for the area and the top 3 hashtags, taken from the hashtag attribute of the tweets returned by the API. The hashtags are taking a while, but they will probably get there soon. Yep, here we are. However, the main purpose of this scenario is to allow users to search by keyword. Let's try searching Unimel. As you would expect, most of the tweets are in Parkville and surrounding regions. When we click on Parkville, we're able to see some Unimel-related tweets in the indicative tweets section. And if we expand the hashtags, we see that Unimel should be in the list. Let's now have a look at some more keywords. Let's first change the keyword to ocean. If we zoom out, we can see that most of the tweets which mention ocean are scattered around the coast, and there is an especially large number of such tweets around the Great Ocean Road, which is here. So this region along the coast here is the Great Ocean Road. However, the map also indicates that the center region of Australia has some ocean-related tweets. This is likely due to tweets which have the location of Australia instead of a specific location. Following the theme, we can also search for a keyword like mountain. Now if we zoom in, we can see that most mountain-related tweets are scattered in areas where there are mountains and ranges. Finally, we can search for a keyword like Costco to get an indication of the locations of various Costcos. So now if we move to Melbourne, and zoom in. As you can see, there are tweets mentioning Costco in Ringwood, which is this area, and there are tweets mentioning Costco in Docklands, which is this area, and so on. Now, let's move on to the sports and exercise scenario. The sports and exercise scenario is very much like the keyword scenario. However, we have associated a list of keywords for each sport or exercise which we have identified to have the most number of tweets. So, we can click on the relevant sport to filter the tweets by that sport. Let's click on exercise to see the areas that have the most exercise-related tweets. From the mentioned sports and exercise pane, we can see that Sydney has the most mentions, followed by Melbourne and so on. We can also cycle through the sports to have a look at the distribution. Now let's toggle it back to all sports. From the pane on the right, we see that East Melbourne has the most number of sport and exercise related tweets. So let's zoom in on this area. Those who are familiar with this area will not be surprised, as it is home to the MCG and some other stadiums. We can also see from the area information that there are 40% of sport-related tweets in this area, which is quite large. Now, let's look at the second area, which is Paddington Moore Park. So this area is in Sydney, so we need to, or near Sydney, so we need to navigate there first. So that is this area here. If we zoom into this area, we can also see that the area is home to the Sydney Cricket Ground and many other stadiums. Thus, the large quantity of sport-related tweets is very much justified. Let's now move on to our final scenario. In this scenario, we integrate the sentiment of tweets, which we pre-compute with IEO and IER values from Oren. This is done by the API component of the app, which takes the output of a MapReduce view, the percentage of positive sentiment tweets for each area, and combines it with Oren data, also retrieved from the database. Currently, the map displays the IEO scores of each area, which summarizes variables relating to the education and occupation levels. From this, we can see that the inner city areas are often more educated. So as you can see, it is darker. It has areas surrounding Melbourne has darker shades, and this is the same for Sydney and Adelaide and so on. The Pearson correlation factor and the p-value indicate that there is strong confidence that there is weak positive correlation between IEO and positive sentiment. Then, we can move on to the IER, which summarizes the variables relating to income and wealth. Again, the correlation factor indicates that there is little to no linear correlation. Finally, let's have a look at what is deployed. Here, we see the debugged print statements of a worker as it finishes the tasks which are assigned to it by the master. If we switch to the summary page, we should also see the number of tweets update once in a while, as it just did then.